So thanks very much to the organizers for putting this conference together. And yet today I'm going to be telling you something about what we can learn about the history of reionization from looking at quasar absorption lines, and in particular the Lyman-alpha and Lyman-beta forest. And so the kind of first point I really want to emphasize is there's a huge amount of information that you can learn about reionization from looking at the Lyman-alpha forest. And a lot of this stems from the fact that if you look at the Lyman-alpha forest along two different lines of sight, so two different directions in the sky, it can look very different. So here's an example of two spectra of quasars at the same redshift. So the black and the red are just two different sight lines. And you can see along one, you see an awful lot of transmitted flux. And another is a completely dark patch for 160 megaparsecs where you see no flux at all. And you can be kind of more quantitative about this and take lots of different sight lines. And rather than talking about the mean flux, you can talk about some effective optical depth measured along some distance. But quantitatively, you get the same thing. And as you move towards higher and higher redshift, the scatter among different lines of sight increases, with some being completely dark and some showing a lot of transmitted flux. So the question is, can we learn something from this? Why do we see the scatter at all? And why does it seem to be increasing as you go to higher redshift? Well, looking just at simple photoionization equilibrium, which is a good tracer of the neutral hydrogen in the Lyman-alpha forest, you can look and you can see what does this depend on. And crucially, it depends on both the temperature and the ionizing background of the IgM. And so people have worked really hard to try and come up with different models to try and understand why these quantities should be so different along different patches and what should cause these large fluctuations. And there's, as I said, lots of different models. So you could have a varying mean free path that causes fluctuations in the ionizing background, or fluctuations in temperature due to patchy reionization. But in this talk, I want to tell you what a late end to reionization can do for you, and hopefully convince you that it's a good match to lots of data that's out there. And so the reason that I'm quite keen on this late reionization model is we've put a lot of work into running radiative transfer simulations of reionization in large 160 megaparsec boxes with moderately high resolution, where we can self-consistently model the temperature of the IgM and the ionizing background. And if we try and look at the mean flux we get from synthetic spectra through these simulations, we find that the only way we can match the evolution of the mean flux below redshift 6 is in a model where reionization doesn't end until after redshift 5.5, and that's the blue line there. And for comparison, you can see in the orange line, that's a model where reionization ends at redshift 6, like people commonly think. And so this is a model that's about 50% ionized at redshift 7, and that's based on trying to also match CMB data. And so if we match this mean flux, we find that we naturally can reproduce the scatter along these of the opacities that it's observed along these different sight lines of the Lyman-alpha forest. So in blue there is the observations that I showed earlier from Sarah Bosman, and in orange are the distribution of sight lines we get from our simulations. And you can see we get this increase in the scatter among different sight lines as we move towards higher redshift. And this is due to this late end reionization, that you have these islands of neutral gas in the intergalactic medium. And obviously, if you hit one of these sight lines, you're going to have a dark patch, where if you don't intersect one of these sight lines, you're going to get a more transmissive sight line that shows a lot of flux. And the redshift where we start to see these sight lines pop up is exactly the same redshift where these neutral islands of hydrogen are persisting down to. So kind of above redshift 5.5, we start to get these really dark sight lines. But I also mentioned that there's these really long absorption troughs in the Lyman-alpha forest, 160 megaparsecs. And they show significant Lyman-beta transmission, implying that the IgM along these redshifts is at least partially ionized. And we can find something very similar in our simulations, where the black line there is the Lyman-alpha, completely dark, and the blue is the Lyman-beta, and you can see we do get some transmission. So you can look and see what's going on. And so these are just along the sight line I showed before is the white dashed line. And I'm just showing three different quantities from the simulation: the neutral hydrogen fraction, the photoionization rate, and the temperature. And you can see this dark sight line is indeed coincident with some of these neutral islands, which are the red patches. But there are little holes. These islands aren't completely fixed. There are patchiness in it, and it's this patchiness that allows these little spikes of Lyman-beta transmission to pop up. But also, like, the IGN is very complicated, and you can see we have these shadowing effects around the neutral islands, and we also get these temperature fluctuations from the different reionization redshifts. So all of the models that I introduced in the beginning are correct in some way or another. But as well as just looking kind of at these sightlines generally and saying, oh, look, we get these dark sightlines with some Lyman-beta, you can also be more quantitative about this. And there was a really nice data set recently from Christina Eilers showing co-spatial measurements of the Lyman-alpha and Lyman-beta effective optical depth. So along the same sightline, measuring both these quantities. And I'm just showing here the data binned in 3 different redshift ranges. And it was shown in that paper that this data is challenging to match with the uniform UV models, temperature fluctuation models, and so on. But it seems that our late reionization model is actually quite a good match to the data, with most of the data points lying within the 2 sigma contours of our model and some lying outside, but these correspond to the long dark trough that I showed before. So this is quite a rare object, and we don't actually produce that many of them in our simulations. So we get good agreement with the observations in this late reionization model as well, which is another plus, but the sample size of the observations is still relatively small. So moving forward, can we use these absorption lines to learn something more about the epoch of reionization? Because everything I've showed so far is kind of below redshift 6. So I'm showing here 2 different simulations with 2 different reionization histories. The top one shows a more extended reionization. So the universe, in that case, is about 50% ionized at redshift 8.5 or so. And the bottom one is a faster reionization, where the universe is 50% ionized at redshift 7. But crucially, both of these models have reionization ending at the same redshift. So again, just below redshift 5.5. So they both match the mean flux below redshift 6, although they're very different at higher redshifts. So you can look and see how these 2 different models compare to the existing data. So the blue here is the fast model and the orange is the extended. And the top panel is the Lyman-alpha measurements and the bottom is the Lyman-beta measurements that I showed previously. And you can see in both cases, the 2 models seem to agree reasonably well with the data over this redshift range, because that's how they were designed to look. What if we tried to move to higher redshift? And so these are now, again, the same 2 models, just now moving up into higher different redshift bins. So going all the way out to, above redshift 6.5. And again, the top panel is Lyman-alpha and the bottom panel is Lyman-beta. And you can see that as we move towards higher redshift, these 2 models start to diverge because you're really seeing the difference in the ionization state of the gas. And it seems that although there is a difference in the Lyman-alpha, most of the difference is at kind of the higher optical depth range, which will be challenging to measure because a lot of the data there is only upper limits. But if you look at Lyman-beta, you still see a larger difference, even at more moderate optical depths, which should be accessible, and that's something that we could actually measure. So it seems like people should really go after these Lyman-beta effective optical depths over this redshift range, because it should be really discriminating for different reionization histories. And so that's something we'd be very excited to see. So that's kind of a whirlwind tour through trying to understand the intergalactic medium in the context of this late reionization model. So the first point, which I think is probably kind of the most important, is if you want to match the mean flux in the Lyman-alpha forest, you need an IgM that's still neutral below redshift 6, all the way down to about redshift 5.3 or so. And once you get that, you find that a range of other observations naturally fall out, including matching the scatter in the Lyman-alpha forest, as well as its correlation with the Lyman-beta forest. And future observations of the Lyman-beta forest will place much tighter constraints on the reionization history. So thank you.
All right, thank you, Laura. So the time for questions. So there is a question from Christine McQueen. It says that the question is that what fraction of the IgM is still neutral at redshift 6 in your work?
Yeah, so it's kind of just around like 10% or so, but it's like all the voids, so the most kind of extreme areas.
Okay, all right. So next question is from Danko. He's asking, do your models prefer Finkelstein 19 versus Robertson 15 reionization history?
So I don't know that I've compared it directly against those two reionization histories, but we definitely prefer kind of, if you include trying to fit the CMB data, we prefer kind of a faster ionization that's ending late. So about 50% ionized at redshift 7 and completely ionized just below redshift 5.5.
Okay, great. And the next question is from the Melema Garelt. The question is that, what does your late reionization model imply for the changes seen in the population of LAEs around redshift 7?
Yeah, so we've looked to trying to model the LAs and their correlation with the Lyman-alpha forest, and we get great agreement there. I haven't myself looked at how the Lyman-alpha fraction evolves, but other people have looked at it in very similar reionization histories, actually based on these simulations, Lewis Weinberger, and he finds that kind of it's good agreement with the observations.
Okay, great. So the next question is from Brant Robertson. In the models that have different tau CMB, but similar tau Lyman-alpha below redshift 6, how do their temperature histories compare?
Yeah, so the model that reionizes earlier, so that has the higher tau CMB, that's cooler just because more of the gas has cooled early or has been ionized early on, so it's had more time to cool. So there is potentially some discrimination there with if you looked at the temperature measurements as well.
Okay, great. So next question is from the Fige one. The question is, what's the tau CMB you used in your two different models, extended versus faster?
Yeah, so the faster one has a tau CMB that's like in good agreement with Planck, so about 0.05. The more extended reionization history would be in disagreement with Planck, so it's more like 0.07 or so. But I think it's interesting to see like how well you can discriminate between these models just using the Lyman-alpha forest. I think that's cool.
Okay, great, thank you. So the next question is from the Xiaohan Wu. So how plausible is it to robustly measure the Lyman-beta for, Lyman-beta forest at such high Z? There must be a lot of contamination from the Lyman-alpha forest.
Sure. So in all the estimates of the Lyman-beta forest I showed there, we have forward modeled that contamination. So that's all taken into account. But yeah, it is pretty substantial. And we also looked at trying to model the Lyman-gamma forest, but there the contamination is just too much. You don't get anything out.
Right. So any more questions from the audience? Yeah, if not, thank you, Laura.
Thank you.
Okay.